A nice way to put it there, Benito. Opposition to the flow of charge. All right, so we'll just work with that definition then. Opposition to the flow of charge. Opposition to current, really, in a circuit or in a material. All right, opposition to current in a material. All right. Yeah, that's it. So at least, you know, you can leave class knowing what, having a better idea of what voltage is and what current is and what resistance is. All right. Important stuff. If you scroll through and see some other questions, you'll see they'll ask you on some papers to explain what is meant by electrical resistance. Also, point to note here that opposition to the flow of current in a material or circuit. This is measured in ohms. Measured in ohms, very important. And measured in ohms. And the symbol for ohms is the Greek letter omega. I think that's the 18th letter in the Greek alphabet, which the Greek alphabet only has 18 letters. So that's the last one. So it's measured in ohms. So those two things you should know about electrical resistance, guys. So, and when you think about electrical stuff, yeah, people start to think about wires, but current can actually flow without wires. In fact, you know, wires are conveniently used because, well, they discover some things about electricity where using a wire would make it more convenient or better. But when you talk about static electricity, there's current flow without wires. There's no wire connecting the sky, or rather the clouds, to the ground, but then there's current flow. In fact, more current flow that way, from the sky or from the clouds towards the ground than from what JPS sent you. So and that's what Ben Franklin was after. He was saying, well, he didn't know how much current was there. He only knows say the current could do something, and he knew that it could convert to another form, and hence he used the jar as to create some light energy there. But electricity was discovered before wires were discovered. While Ben Franklin was in the US celebrating independence, on July 4, they had Ampere in France was studying wires. Actually, he was saying, well, you had a guy who Volta in Italy, Alessandro Volta, they named the voltage unit from. So he was in Italy making batteries. The first battery on earth he made using salt water and coins. All right. So that's something that you could try at home, really. You just get some salt water and get like a little tissue or something, and get like 2 coins, maybe $1 coin or something. But what he did, I think he used 2 different kinds. If I remember clearly, I could probably find that find that literature and show you. But that's what he used to make the first battery, and then that was when electricity became a thing in his time. We're talking about 1700s. So that's when all of what we are learning now was discovered. George Ohm was from Germany. So we find out that different people come into play to build this topic of electricity. Man from Germany, man from France, man from Italy, and man from US. You know, when all was said and done there, Jamaica got its first electricity in 1872 in Black River. So it was like 100 years after this was going on. So, it's very important for us to know here. All right. So, any questions here, guys? No. All right. So, we're gonna leave it with that though. Because I did send a lab though. I sent an activity there. There is an app that when you go on it, in fact, let me go back to that thing. I'll just save this for you and send it here. All right, so I did that. But the paper that I sent to you seems to be here. And it started out by actually telling you what it is. It's Ohm's law. Now, this is a good place to start. Right? This is a popular CXC question, state Ohm's law. All right. It's actually saying here that the current flowing through a metallic conductor held at constant temperature is directly proportional to the potential difference between the ends. So potential difference is voltage. This means that current is affected by the voltage. So this is something that CXC tests a lot. Remember, voltage is from the battery in the form of EMF. And by the time it reaches throughout the circuit, it becomes potential difference. So really, voltage is a term for both of them. But this is actually a device that used to measure the current called the ammeter. And of course, this V measures the voltage. It's actually a voltmeter. So these are things here. All right. So for this now, basically, you're going to basically read through this. As it says, read the theory and watch the video links. All right. Aside from the video links, you're supposed to get some data from it though. But the resources part here is important. This app here, you see the second resource here, this is actually an app. And I'm going to show you what it looks like though. Just before you guys leave here and see if I can get a zoom on it and switch the screen and show you. All right. So so we're here sharing this screen too. Everybody seeing this?
Yes, sir.
All right. All right. So what you should be seeing on the screen here is it's a concept. It's a very same Ohm's law here actually. Ohm's law basically say V equals IR, or voltage is equal to the product of the current times the resistance in a circuit or in a conductor. And what happens here is that, all right, the current is dependent on how much voltage you apply and the resistance of the material you're using. All right, so that's why this app is set this way. Notice that these are in blue. This is showing you what is affecting the current. Current in red to show that it's actually a responding variable here. So the current I, and why the symbol I is used for current is that, well, I stands for intensity of current. So that's why I is used for current. But in this app now, what you could do is just vary the voltage. Realize that as I increase the voltage, what is that? All right. So every time I increase the voltage, what happens to the current?
Increase too.
Yep. That's what Ohm's law say. Voltage is proportional to current. So if I increase the voltage, I increase the voltage, I increase the current. Increase the voltage, increase the current. Notice that I didn't trouble the resistance. Right now, the resistance that you're seeing there is at 10 ohms. The voltage is at 0.1. And then the current here is at 1.0. So what they're saying, actually, there's a formula that relates. And actually, this is the formula, really. So we would actually put this in a triangle and say, well, V at the top and I, and you have R, and then you get some questions to calculate the current in something, or the resistance of something, and or the voltage through something. Those are what you use, the V equals IR. So this is Ohm's law. All right, so and so that's where it is. So now increasing the voltage, increasing the current. Notice that I can't trouble the current, none at all, because it is so dependent on the voltage. You have to force the current. So therefore, as the voltage you adjust, not the current. So The resistance now, I can change the resistance, making the material more. All right. Look at this now. If you notice, in this is a circuit that's shown down here towards the lower left hand side. We're seeing that there's a battery source here. If I were to increase the voltage, you realize the battery gets bigger. All right, and you could relate this to even your phone, because, well, that's why phones have gotten slightly bigger over the years, because it's really the battery that causes the phones to get bigger over the years. You need a better battery. Notice that you have it, right? So notice that this is the batteries that actually increase in the voltage.
Sure.
Yes, go ahead.
Even care battery you can use. Because me try one terrestrial battery if you jump on Prado and it never did work.
Exactly. The size of the battery is important to the size of the current the object needs. So yeah, truck battery. Prado probably use more. But I can tell you though, it depends. But it was it a new battery you used though?
Yes, sir.
Okay. Well, yeah, batteries do have their limits. Batteries do have their limit. They have their limits in terms of voltage. So that's what happens there. So you probably certainly need more power to start the motor that's in there. And when you reach the alternating current part, you'll understand how that part of the car works. All right. But all right, guys. So this is just an introduction here to current and voltage here. So and this is optional apparatus. This is what I'm using on the screen now is really it's the FET app. So I could send this to you. As a matter of fact, let's try and copy the link so that you guys can go on it and try it out for yourself. All right, so let's put it in the group. And there you should see it shortly. All right. Oh, I don't know. Oh, I have to delete it because you know, copy good. All right. Let me just copy that part here. And then if you fix it up. All right, it's supposed to be hyperlinked, so if you're not seeing it hyperlinked, then I'm going to repaste it. All right, this should be the correct link. Yeah, it is. All right. So everybody seeing it?
Yes, sir.
All right. So yeah, that's it. All right. So when increasing the voltage, increase the current, resistance remain constant. All right. Well, if I were to increase the resistance and look at the value of the resistance here, 598 ohms, it can go up to 1,000 ohms. All right. But we notice that if we increase the resistance and don't trouble the voltage, the current, how is the current responding?
Decrease.
Very good. Current is
Sir,
decreasing.
decrease.
It decreased. All right. So increase the resistance, the current decreases, you say? All right. If I decrease the resistance, what happened to the current?
It increase.
Yes. Very important relationship to remember, guys. All right. Very, very important. Extremely important. So so that's what I wanted to leave here tonight, understanding Ohm's law. All right. Basically, what you just say a while ago, it's Ohm's law. All right. So voltage. All right. So an increase in voltage will cause an increase in current. However, an increase in resistance will cause a decrease in current. The fancy way to say it is just to say that, well, voltage is directly proportional to current, but inversely proportional to resistance. So that's the story there, guys. All right, so that will be it. So you guys have any questions?
No, sir.
No? Okay. All right. So All right. So for those of you who wanna do the lab here, you basically going you basically just going to use the app, all right, and like you're going to use different voltage values, keep the resistance constant, but just record the values of current and voltage in the table. Let me just switch over to the other screen and show you what's happening. All right. So you see this table here, guys?
Yes.
Yeah. So you're going to use the same app where I sent in the group and try and use different voltage values and record the current, the responding current. And you're going to basically plot a graph and see if you get a straight line and answer these questions. Explain the meaning of the terms current, voltage, and resistance. State Ohm's law. Describe the shape and trend of the graph obtained. And of course, there's a gradient for you to find if the line is straight and deduce whether or not Ohm's law is verified. So this is something that we can talk about in the group, or you can text me if you have any questions here. All right. Very simple, Abdo. So just follow through. All right, guys, um and that will be it for tonight. Seeing that went some overtime because we start late, but trying to give you back the time. And also I need to announce to you guys that for the month of May, we're going to extend the class times. All right. It's now or never. So we have to extend the times because they're not always available on weekends. And in fact, this weekend I might not be available. So you know, if we can next week, if we can extend the class times, I'm giving a heads up. All right. So who going to say, well, they have to go to other classes? Yeah, you go to those, but I'm just announcing that I'll be extending the classes. So be prepared.
So this have to do what you have to do, so for that have to go on.
Yeah, yeah.
Exactly, sir.
No problem there. All right. So yeah, at least understand what is at stake here. So well, all right. So this is it. This is it. Really sorry I didn't start electrical before, but I had to sacrifice it because the last part of the syllabus needed some attention. So I actually went there, and then now you have this year. So I just say no, pretty soon I just say it will all be past papers. These lab sheets will be over with, and then it's just be past papers after that. Whatever we not learn yet, we'll learn it through the past papers. Like the one I started out with showing you. So let's see something here. So we can find it back. Yeah. So no, this actually was a paper 3, so a lot of concepts come in here. All right. The things that underline here though important still, no guys. This here with the all right, the current, the voltage, and so on. But the circuit symbols, they will ask about it. So them ask you down here, so them ask you what later, what type of component is used here. So when you're talking about electrical stuff, you need to know the symbols for the different electrical devices. And that's something we're going to talk about in other classes. But you might want to start now because it's actually in the lab. And trust me, there's more where it came from. So battery with parallel lines here. All of these lines what you see here is just connected wire. So you'd label A as a battery, and then B would be well, what the circle here be something measuring the current. All right. So this should be an ammeter. All right. Just filling out this for you like oh it's the first time you've seen it. So A is battery. All right, I'm sending this paper to you. So A is battery, B is the ammeter. I think a 2M in ammeter still. Not sure. And then of course when the current flow through the ammeter, some of it going branch off, it will split. So another thing you will learn about circuits is that circuits have junctions. And when where there's a junction in a circuit, the current split. So and when talk about all of that some other time, but just remember that sir told you that the current split when it reach a crossroad. All right. So all right. So now This here now, it's actually a voltmeter. All right. And let me see what's happening here. Okay. Yeah, that's a voltmeter. Reason being, voltmeter, it is measuring potential difference. So one side of the voltmeter is connected here, the other is connected here to measure the difference in potential when the current pass the 2 points them. All right, so it's measuring the potential before it passed through this thing we label R, which don't know if anybody can guess what that R stands for, but certainly the R would stand for resistance. So yeah, so it's actually a resistor, really. That's the device. Resistance is what it does, but the name of it is a resistor. All right. So the current now split. Some go to the voltmeter, some pass through the resistor, but then the voltmeter is measuring the difference in potential between these 2 points. So that's why it's placed there. Current still continues to flow here. Remember, I flow from the plus sign to the minus side, and it's meeting on this device here, labeled D. All right, so this is actually called a variable resistor. It's like a knob that we use to turn things. So like probably a radio or something like that. It's used a variable resistor. And then of course E. Anybody can guess what E is? E. Oh, yeah, okay, Dwayne. You said something? What you said, Dwayne? Switch? Yeah, very good. All right, so you know the switch there. At least know that. What on earth is C? Okay, I put it here. It's a voltmeter. And so that's it. So these are the little questions that CXC could ask you. You don't want to miss out on these. But electrical components is a major deal for CXC. And of course, afterwards, I can give you a result table like what you're going to get from the lab, and you're going to plot a graph with it. But this is also like a taste of how CXC sets electrical questions, all right? Hopefully I can copy all of this and send it to you. So that valued 5 marks in the year that they send the exam question. All right, so not getting everything selected here. Let me just zoom out a bit and see there. I think it's better to. All right, and if I can just group it. All right, that's allowing me to group, but allow me to save it as a picture. And that's Ohm's law question. All right, and let's go here. All right, let's see. All right, we're still on that third screen. Let me go up on the second screen now. So I'll go on. All right, if I press F11. All right, there you go. So in a short while, you should be seeing it in the group. I get all these things together here and send it to you. All right, so all right. Yeah, you should see that now. All right, so that's over there. All right. And of course, let me just put the date here because the date for this now would be today. So let's put it at the 6th or the 5th, 2021. All right. This probably will be lab 9 for you guys. All right. This is something. This is on that. All right. No. I'm trying to get person on board. All right. So that's it now, guys. So send you a lab, send you the link where you can do the virtual lab. And I should send you this to know the topics I want to need for study. the exam for electricity. All right. CXE claims that they're going to release the topics, some topics a couple weeks before exam. Yeah, if they do that, well, you know, that would be nice, but not necessary because those who study in the exam year after year would know exactly what would be coming anyway. All right. Let me save as picture. I'm going to send this to you as well. Probably help you to prepare for exam. All right. So this is electricity topics. Yeah. Yeah, well, sure. All right. And all right. And this should be sent to you guys. Where is this now? All right. So electricity topics. All right. So all right. So all of that is in the group now. All right. I think this is it. All right, guys. So that is it. All right. No. Anything else? I think that's it. All right, guys. Well, thanks for making it out tonight. Despite the lengthy delay, you guys came out, which is commendable. 10 persons, not bad. And as I say, you guys need to think this is the only group I'm not seeing. Are there anybody meeting outside of class time? I know that it's happening for chemistry, but certainly not for physics. Anybody linking up?
No, sir.
No. What you guys waiting on? I mean, we have Jenna not here tonight. So your class decided. Jenna.
Sir, no said that, but just said on my mind. I swear to God.
All right. Yeah. So Jenna not here, but it would have been nice if he was here. As usual, Antonio not spectating tonight. He very, very occasional. But all right. So you know, guys, I don't need to group up, man. I don't need to group up and start out the thing, you know. I mean, that makes sense. Chemistry students grouping up. So my engineer do chemistry. The HNL, you know, it go already.
Yes, sir.
The Bora as well. Wait, who else was at the chemistry meeting? Apart from the HNL and the Bora figure. Benito, you were there?
No, sir. My school friend and we are running a little marathon.
Okay.
We work some past paper.
Okay. So you're otherwise engaged then. All right. About Michaela. You were there?
No, sir.
Oh, okay. All right. That's cool. Shantai, you were there? Shantai? So Shantai left your computer gone. Got that. Daniel, you can get in on it as well, you know. You know of it?
Of what, sir?
Of what? The meeting.
Oh, I didn't. Sorry, sir. I didn't hear what you said the last minute.
That's me. Oh, you're distracted.
Yes, sir.
All right. Anyway, but you guys need to get to know act together still. So I don't know, and you know, physics is a little bit need more, a little bit more attention on chemistry. I would say still, but all right. But you guys just take care of yourselves, and I'll see you next time, whenever that is.